Hi, everyone. Thank you for joining our webinar today. It's one in a series of webinars from Atomic Enterprise Platform. We actually have a great topic today, and one I think which garners a lot of attention from customers. That's on networking, and particularly the software-defined networking and virtual networking that is required to connect containers together across several different nodes. Our presenter today is Eric Paris. Eric is one of our principal architects on the Atomic team with a primary focus on Kubernetes, which sometimes to his dismay also includes the full networking stack that we'll be covering today. First, I want to hit the disclaimer. Just a reminder that this is part of a technology preview, and so as such, the content set forth herein does not constitute in any way a binding or legal agreement or impose any legal obligation or duty on Red Hat. This information is provided for discussion purposes only and is subject to change for any and no reason. Next slide. For those of you that have been joining us throughout the series, welcome back. For some of you who may have stumbled upon this in your first, keep in mind that this is one in a series of webinars, and Atomic Enterprise Platform encompasses this entire stack. And as with previous webinars, we do deep dives, but also the first one is a very high-level overview. I actually have a link provided at the end of the deck if you want to go back and take a look at those things. But just keep in mind that Atomic Enterprise Platform is a container orchestration service that encompasses orchestration, cluster services. It has a built-in registry for containers. There's a lot of automation built in. And of course, on the next slide, you'll see that our topic is networking. And so before I hand it off to Eric, I'd like to encourage everyone to ask questions in the chat. I'll be watching there and can answer occasionally when things come up. But also there will be some time at the end of the session for Q&A for Eric to respond. So keep that in mind. And without further delay, I'll hand it off to Eric. Go ahead.
All right. Thank you, Mike. As he said, my name's Eric Paris. I'm our lead for Kubernetes is a part of the Atomic OpenShift effort, and the networking team, and a couple of other areas. Today, though, we're going to talk about networking as it relates to the Atomic Enterprise Platform. We'll talk about why we did what we did. We'll look at some of the reasons that's beneficial. Some of them, they aren't so beneficial. Reasons you might wish to choose a different set of trade-offs than we did. We'll see how we move traffic about. We'll do a little bit of demo and then talk about what you can do if something goes wrong. For this talk, I'm expecting people to know what a pod and a service is. A pod is just one or more containers launched by the Atomic Enterprise Platform. A pod, like I said, could be multiple containers. For the purposes of this talk, the important thing is those containers share a network namespace. They all see the exact same network stack. Services being the other one that hopefully people already understand. We will talk about it a little. Services are how pods are able to find other pods. It's label-based. Pods have labels. Services are able to select certain sets of labels and then find the pods with those labels and route traffic to it. Just so everyone knows, those are kind of my backstory. So why do we need this software-defined networking thing? Well, one of the things that we have done is made the decision that all pods get an IP address. We're not going to do any type of well, there is some magic port forwarding, but not at the application level. We're not going to do that type of magic port forwarding or overloading, or your web server can listen on port 80 if that's how you set it up, and you can deploy 300 of those web servers all on the same node, all listening on port 80 because they all get their own IP address. So one of the things that's required when we say all of these pods get their own IP addresses, they have to all be able to talk to each other. Trying to get these IP addresses to talk to each other is not necessarily so easy. Most organizations have entire networking teams trying to get IP addresses able to talk to each other. And now we're trying to make this very mobile and ephemeral. So the way that we, using our software-defined networking, are trying to make that easier for you is by moving that networking into the nodes. So you only need the nodes, control of the nodes, in order to make this work. in the physical world, that what we're trying to build will be the equivalent of every time you start a new application, it's actually a whole new computer almost, right? You're going to have to plug in some cables. You're going to have to set up your managed switches to have the right new machines that you created able to talk to the other correct machines. You're going to have to set up firewall rules. And when you pick up a machine and carry it to someone else's desk, rack, wherever, and plug it in, it all needs to start working again. This is pretty difficult to do in the physical world, especially since in the Atomic Enterprise platform, we expect these things to be able to come and go at very high rates, unlike the traditional IT infrastructure where you turn on a computer and it sits there and runs for 3 years, and every time there's a problem, you baby it back to life. We expect these things to be able to come and go much more rapidly. But in Atomic Enterprise platform, we're basically doing the same thing. Instead of a physical machine or even a virtual machine, we're starting a pod, right? We're attaching that pod to an quote-unquote Ethernet switch. In our case, we'll talk about some of these words later. We're using Open vSwitch as our quote-unquote Ethernet switch. We're using VXLAN tunneling in order to connect these IP addresses on different nodes all over your cluster, these pods on different nodes all over your cluster, and make sure that traffic is able to flow as it wants to flow. We provide some of the ability to control how traffic comes in and out. The really neat thing is that we can do all of this automatically and with very little management on your part. There are other people, other companies who provide similar SDN solutions to solve in this space. Today we're going to talk about OpenShift SDN, but there are others who are providing SDN solutions in this space that can be used with Kubernetes and Atomic Enterprise platform. Docker has its own networking model. Their networking model is largely based on the Docker orchestration concept, which the Atomic Enterprise platform is not built on. So the Docker lib network things don't really apply in this space, just for a heads up. So I said I'd talk about some of the technology involved. There's often misconstrued, people will be like, oh, well, you're using OVS instead of UDP encapsulation. Or oftentimes when you read about SDN, some of these words are used together where they don't make sense. Our solution, OpenShift SDN, uses OVS as its virtual Ethernet switch. OVS is a highly programmable in-kernel switch, well, with sort of in-kernel user space drivers too, much like a high-end managed switch. You have all sorts of controls on if something comes in on this port and it matches all of these things, it's allowed out these ports, very flexible. Most people are used to the Linux bridge, using bridge control and commands like that, which is more like a dumb unmanaged switch. Things come in on the left, they go out either on the right or everywhere. That's all you can do with the Linux bridge. So we make use of Open vSwitch. There are others who make use of the Linux bridge. So how do we get traffic between nodes, right? I mentioned that we use an encapsulation and tunneling. We use VXLAN. So when a packet comes out of a pod, we will encapsulate that packet into a VXLAN packet and send it across the physical wire in VXLAN. That means that the physical network, the actual network that your network admin group manages, will never see these pod IP addresses. They'll never have to know about these pod IP addresses. They never have to be involved. There are obviously other choices that others have made. VLAN tagging is something that people do. There's hardware support in a lot of managed switches for VLAN tagging. If you do VLAN tagging, you can make use of your hardware, but in that case, you have to actually work with your network team has to work with you in order to set those things up. Whereas like VXLAN or UDP encapsulation is done entirely in the node, and you need no buy-in from your network team whatsoever, and it just works. Other people use IP routing, which is sort of a good idea. But again, if your nodes cross a layer 2 broadcast domain, that means that the routers in the middle are going to have to participate in the IP routing, and not too many organizations or the network admins willing to pass routing information to the sysadmins and accept information from them. It's just not generally how that works. And the other kind of sets of technology that are often talked about, the vEth pair. So when we create a pod, we create a virtual Ethernet pair. We stick one side of that pair into the pod. It shows up as ETH0. We stick the other side of that, this is a lot like an Ethernet cable, into the OVS bridge. If you have looked at many of the KVM, QEMU-based virtual machine solutions, you'll often see the tap-ton driver, which is sort of similar, except one side of that's in user space. That's not what we make use of. We make use of vEth pairs. So why do we use all this stuff? I'll tell you, the biggest one is that last bullet point. Things just work. That's really the biggest reason. You can take nodes. They don't have to be physically near each other. They don't have to be in any way similar. You can have one node on one cloud platform, another node on a second cloud platform, and the third node can be your local laptop. You obviously have no control of the underlying network infrastructure between those three nodes. And you can start AEP, and our SDN network will set up tunneling between those three nodes, and things just work. You can spin up pods. They can talk to pods no matter where they are. Everything works seamlessly without any help or any coordination with the underlying network infrastructure. So that's a wonderful thing, not having to work with the underlying network infrastructure. It just works. There are some drawbacks to that, right? Networking hardware does provide some benefits. In using OpenShift SDN, there are two, I guess one main, one kind of small drawback. The first one would be, because we're encapsulating every packet that comes out of a pod that has to travel across this VXLAN overlay, that means we have to reduce the MTU just enough to put that encapsulation header on the front. That means instead of 1500 byte frames, you get 1450 byte frames. For most people, not a huge problem. Jumbo frames can work. Instead of 9,000, you can get 8,950 byte frames. So this one's not a huge drawback for most people, but something to take note, and sometimes MTU problems can crop up. The bigger drawback to all of this is doing that OVS encapsulation requires CPU time. Every packet that comes out, the kernel has to figure out where it's going, has to stick this header on the front of it, has to send it across the wire on the other side. That machine has to find that VXLAN header, pull it back off, figure out where it needs to stick it in. So there's CPU time that comes because of this VXLAN encapsulation. When we're talking about 1 gig NICs, our performance tests find that this encapsulation is largely irrelevant. As you start needing to use multi-gig NICs, this encapsulation overhead, the CPU time needed to do this, becomes more meaningful. There are actually hardware NICs that do VXLAN encapsulation. With those NICs, we have seen incredibly high throughput with little CPU impact. But that is the bigger, or kind of biggest disadvantage to using an overlay network, is the CPU performance impact of encapsulating and decapsulating frames. Are there other people out there, other things you can do? Yes, like I said, hardware accelerated NICs exist, and they are awesome. They are enabled by the RHEL kernel, and thus those features work in Atomic Enterprise platform. There are, like I said, other vendors that provide network SDN solutions that are compatible with Atomic Enterprise platform. Those people, such as if you were to work with Nuage and you had hardware from Nuage, they're able to take advantage of their hardware. You remember, our primary motivator is works everywhere for everyone all the time. right? That's our number one priority, is that your system will work and you don't have to have support of your network infrastructure. So this picture shows us all the different little pieces and parts, almost all, that go on inside a single node. The external pods over on the right and the external systems over on the right, those are actually external. Everything else is in your one node. What's going on here, we have this OVS bridge on the left. When you create a pod, inside every pod, they're all going to see ETH0. Remember, this is a different ETH0 than the actual ETH0 on the host with the cable coming out of the back of your piece of hardware. But inside a pod, you'll see an ETH0. It'll have an IP address. It'll be unique across the entire cluster. There's a vETH pair that plugs into that OVS bridge, right? If you launch a container with Docker directly, Docker is not very capable in its networking functionality. It can only understand the Linux bridge. Thus, Docker containers that get launched manually, they get plugged into a Linux bridge, which we plug back into our OVS bridge, so we can do intelligent things with the containers that you may launch outside of AEP. If you kind of look at this, if pods are trying to talk to an external service, they will have to go through some NAT and then out over the network to get there. If they're trying to talk to a pod somewhere else, they'll get VXLAN encapsulated, what we were just talking about, and they'll travel over the external network VXLAN encapsulated. They'll then get de-encapsulated on the other side and end up at the external pod. But these are the basic things that go on inside a single node. So this is sort of what goes on in the whole system, right? On the left, we have one node. It's got 3 pods running. It's talking to some other node that's on a completely different network. These IP addresses are obviously arbitrary, but I just wanted to show these nodes don't have to be on an L2, like a single broadcast domain, right? These nodes can be absolutely anywhere across the world from each other. And what actually happens is the pods on these 2 nodes will talk over this overlay network, this 10.1. whatever network. Obviously, these addresses are configurable. But pods will, from the pod point of view, they're talking directly to the other pod, which is that little blue overlay network. In reality, what's happening is between the server on the left and the server on the right, they're getting put in that VXLAN overlay with the encapsulated packet and being forwarded across the network in whatever way and decapsulated on the other side. So a big problem with this, or you know, not big problem, but one of the things that's most important or whatever, and we'll go over all 3, is how do I get traffic from, I'm going to jump back. How do I get traffic from this little guy who's sitting in his laptop into a pod? That's obviously something that needs to happen. And I told you that the real network knows absolutely nothing about the pod IP addresses, which means the little guy at his laptop can't be using a pod IP address. So how do we get traffic in? We'll cover that. How does traffic get from one pod to another pod? How does it find that other pod? What happens there? We'll talk about that. And then how does traffic get out? Like I said above, you can go from a pod to some random external database or something. How does that happen? So getting traffic into the cluster. This is that little man from the outside trying to get to a service, a web server, a microservice, or whatever that's running inside. There's generally about 3 different ways. The first way, that the most, I think, important for most people way, is what we call the router. It wasn't an adequately overloaded term, so we decided to use the word router for this. The router is an Atomic Enterprise platform feature in which you can give a stable DNS name to that guy with his laptop, right? He will go to, and we'll demo this later, www.example.com. It will hit the OpenShift router. The OpenShift router is able to participate in the SDN, knows all about those pods in the back end, and he's able to forward traffic to the correct pod in the back end. if you download Enterprise Platform, you run the Ansible install scripts, you will, like out of the box, get a router set up and running based on HA proxy. It's actually just a container on the node, really simple to get running. The HA proxy and router support only supports HTTP, HTTPS, and TLS traffic with the SNI extension. It has to know for encrypted traffic what it's destined for. And if it doesn't know where it's going, there's not a whole lot it can do, which is why it only supports those. There's work to support other things coming. So another option, if you need to support non-HTTP-like traffic, is what's called the node port. Node ports are kind of yucky, and by kind of I mean very. When you declare a service with a node port, that port, every single node, all of the nodes in your cluster will start listening on that port. And if you hit any node in the cluster on that port, it'll get forwarded onto your application. Now, your application might be on node 1, and the end user hit node 7, port whatever. He's going to go to node 7, port whatever, and get forwarded back to node 1, port whatever. But this is arbitrary TCP and UDP forwarding port-based. It hits every single node in the cluster, which actually can make it really easy for you to set things up. You can just tell customers use this node or these 2 nodes or whatever, even though it's listening on every single node. Another mechanism, there it goes. Another mechanism for getting traffic into the cluster, it's what's called host ports or host network. A pod that's declared with host network is literally, this is not some figuratively sort of using literally for what it used to mean, using the same network stack as the host. There's no magic here. If you use host network, your pod is exactly the same as if you launched that application on the host outside of a container from a network point of view. It's not like it forwards to the host network. No, it is the host network. That means that host network has absolutely the same performance characteristics as an application running on the host. Right? Absolutely the same performance characteristics, which is wonderful. We run our HA proxy router as host network. So the HA proxy uses the host network. It listens to port 80 and 443 on the host, on the actual host, and then forwards traffic inside. Host ports are similar to host network, except for your container is only listening on a specific port. It actually does get its own network namespace, and ports get forwarded into it. But when you use host network, earlier I was saying every application gets its own IP. That's not true with host network. You literally get the host IP. So this is kind of a picture of, of that router ingress. The guy on the outside, on his laptop, he's going to connect to the public IP address of your router, of your external node. That's going to be typically a DNS entry, www.example.com. The router will know about where the pods are on the back end and will forward that traffic along. All right. Traffic inside the cluster, how do you get from pod to pod? Well, pods can just talk by IP, nothing special there. But these things come and go. You might have 3 1 minute and 4 of them the next. How do you deal with that? It's dealt with services. Hopefully, like I said, services are something I hope people already know a little bit about. Services use labels. Pods have labels they can say, as we'll see. I think I called it tier equals front end was my name of my label in our demo. And so if one pod uses that front end service, or their traffic will get forwarded to a pod that provides that service. We automatically create DNS entries inside the system, not outside, inside the system for these services. We also expose services as environment variables inside a pod. So there's multiple ways that the individual pod can learn about the service. So getting traffic from a pod to, say, an external database, an external DRM system, something you have running outside of Atomic Enterprise Platform. Well, actually, it just works. It's really simple. We NAT from the pod's IP address to whatever host's IP address it's running on, and traffic can just go out. You can actually use the services mechanism to represent that external address. You can use whatever. You can hard code the IP inside of your application, whatever you need to do, but it's really simple. So let's go back and talk a little bit more about that router, because it's the interesting thing. We often suggest to customers that they use a wildcard DNS entry to the router. So your DNS would be for like star.example.com. I know that a lot of organizations don't like wildcard DNS entries, which is fine. You can, outside of our system, configure your DNS route by route. You want to create www.example.com, you go to whoever owns your DNS system, you tell them www.example.com points to my router nodes. You want to create hello.example.com, you go back to them and say, hey, point hello.example.com to that exact same thing. You just keep doing that, which is fine. But outside of our system, DNS is not automatic. Many customers find that wildcard DNS to be a lot easier to deal with. Like I mentioned earlier, the number of protocols that our router can handle is limited to web-like protocols. So this is an actual router object, and it's actually the object I'm going to use in my demonstration. This is the entire thing that you would tell Atomic Enterprise Platform, and it would start making www.example.com work. Now, admittedly, you had to already launch the web server, and you had to already launch like the service for that web server. We're going to see that in the demo. That's not hard. But this is the entire router configuration that we'll use in the demo. There's no dark secret difficult magic here. It's got a name so you can identify it. It's got this host line. You're telling the router, this thing is going to reach you as www.example.com. It's up to you outside of Atomic Enterprise Platform to make sure www.example.com gets to the router. And on the back end, it's going to go to a service called, in our case, service name. Really simple. That's all it is. The router can handle TLS, like I mentioned. In all three major variants, we can edge terminate, meaning it'll be encrypted from the end user's laptop to the router and be clear text from the router to the back end. That allows you to write simpler backends with less processing power and do all of your encryption stuff out there on your load balancer that was actually built for that sort of stuff. We can do pass-through, right? If you have SNI headers, the HA proxy is able to tell where it needs to go, even though it doesn't know how to decrypt it. It can forward it in, and then the back end can take care of it. And we also can do the re-encrypt, where the front end will decrypt it, figure out where it needs to go, and then re-encrypt it so that while it's inside AEP, it's encrypted, although differently encrypted than on the outside. This is on the right side is the actual route object. You'll notice it looks very similar, except for it has this TLS section for an edge terminated forwarder. You just have to give it the information about how HA proxy or whatever your router should be. I should state that we actually provide plugins for the F5 Big IP platform as well, although out of the box software HA proxy is what's there. You have to tell it the keys that you're going to use to terminate that route. So I'm going to do a quick demo of this stuff, and we're going to talk about kind of four things in this quick demo. I'm going to show pods able to talk to each other. They're going to be on different nodes. They'll have different IP addresses, and they're able to work. I'll show pods talking to other pods via services, right? Because knowing another pod's IP is hard. If that pod went away and came back, it could have a new IP. It's not stable. but services are stable. So we'll see services by IP, by DNS name, whatever. We'll see the router in use. You'll see my laptop actually able to go to, in this case, www.example.com and see our application. And then we'll show how all of this together can allow you to, say, roll out a new version of your website slowly to only a couple of customers at a time. So we will come down to the demo and make sure that I'm in a project. So right now what I'm doing is I created 2 pods. That's all I did. All the pods are doing is sleeping. They're actually going to sleep for 1 day apiece. They aren't quite up yet. This command looks long and scary. It's really not. This template thing is just so I can get it to print out just the information that we want. Oh, one of them's up. And now they, well, should both be coming up. This is not what's supposed to happen. Let's try to create a third one. We will try to create a third one. I'm not sure why that first one isn't coming up. So, wonderful thing about these systems, these things are all pretty ephemeral. That third one's going to be slow coming up. There we go. Now I have 2 of them alive. I'm not sure what's going on with R2 there, but not really important for these purposes. So OCExec allows you to run a command inside of a running pod, no matter where it is on the system. So if I wanted to, I'm inside this pod down here, and I should be able to ping the other pod, right? There's nothing all that amazing about this. Just 2 pods. They're running on different nodes. We see this one's running on this node, and this one's running on this node. Nothing all that interesting. They're able to ping each other, which is what we wanted, right? We want pods to be able to talk by their IP address. Now I'm creating another replication controller and a service that will point towards that replication controller. So, oh, good, that pod finally came up. So that hello replication controller, it created 1 pod. It's the hello OpenShift pod. These 3 are just sleeping. They're doing nothing. They're just sleeping for a day. This one is running a little web server that says hello OpenShift. I created a service that pointed to that, a service that points towards this pod. But once it gets an IP address, and it's not coming up for some reason. This is a bit of a problem. Well, give it a second. I guess it's having to do a Docker pull. That's usually why it's taking so long. Yeah, it says there's a pulling hold. In any case, I thought I had all of these pre-pulled. There we go. Now the pod finally came up. Docker pull just taking a little while there on the back end. So I should be able to, from any one of these, I should be able to check out the hello OpenShift. Now, hello OpenShift is running on port 8080, just because that's the way that pod was made. And there we go. I talked from 1 pod to the web server that's just, all the web server does is say, hello OpenShift. Nothing all that interesting about that. So we aren't using the service there. All we're using is the pod's IP. Now, if I look at the service, I can, instead of hitting the pod's IP, I can hit this stable service IP. And the service is listening on port 80. So even though the pod's on 8080, the service is on 80, and we should actually get the exact same result. In this case, the pod is hitting the service, this stable IP address, this better port number, and even though the pod is this random other IP address and port, traffic's able to get there. That's nice, but again, you have to know the IP address. So I was saying, how do IP addresses get into pods? Well, the biggest way is by DNS. So the service has a name right there. I should be able to, now it's looking up that, so we're kind of jumping into this pod somewhere in the network. We're looking up the DNS address. That's giving us this service address, and then we're running back to the pod. That's actually, the full name is, what is it, project1.service.cluster.local. I think that's the full name, just so you can see how that works. Oh, that's not what I wanted. I wanted an actual pod. So if I were to look up that address, that P1 hello service, you see that it's pointing, the DNS entry was automatically updated to point to this stable service address. So that's how those work. All right. So now right now I only have one of these things backing, one of these pods backing the service. What I did here was I just said, instead of one hello OpenShift pod, give me 2 hello OpenShift pods. Now if I were to, assuming it came up in a reasonable amount of time, yes, it did this time, I see that my service has 2 pods behind it. So the exact same service, because I duplicated the number of pods, is now going to round robin-ish. It's a statistical round robin. Talk to 2 pods on the back end. So what this is showing me, this long command that is only long because I wanted to print specific output that's easy for us to read, shows me the labels on the pods. So these hello pods have app equals hello, tier equals front end, right? There's my 2 copies that I said. And then my sleeping pods, I just called those app equals sleep. My selector on my service says any pod that has tier equals front end, which if you look down here, we have tier equals front end, is what it's going to load balance to. So you can't necessarily tell from this command that when I run it twice, that one time it's likely to have hit one of the pods and one time it's likely to have hit the other one of the pods, because they're doing the exact same thing. But trust me, that's happening. So just to show that I haven't, so this is all running on my laptop. This is on, and these machines, these physical machines, are actually hundreds of miles away. I'm not quite sure where they are actually. But if I go to www.example.com, you can see it's not there, right? It doesn't exist. It's not returning anything. But I'm going to create a route, right? So now I'm doing that, how to get from my laptop to something inside the cluster. What I was doing before is I was executing inside a pod already running on the cluster. So all of that was inside the cluster traffic. Just to show that there's nothing special in this route that I just created, all it is the same thing I showed in the slide. It's got this hello one route. It's a service backed by this same service that I was playing with earlier, right? This service here that I was looking at earlier, hello service, right? So what I just did here was jumped over into the project where the router itself is running. So this is an HA proxy is running in this, HA proxy is running in this project, and we can see the HA proxy configuration that Atomic Enterprise Platform created automatically is pointing to these 2 pods that it's the same 2 things that the service are pointing at. So now I've created this route. HA proxy was automatically updated. Now here on my laptop, if I go to example.com, we see, hey, look at that. I just hit those pods that my laptop knows nothing about 10.1.2, like totally clueless. My method of cheating is I pointed my Etsy hosts at my routers. All right, those are my routers. Those are not pointing towards those pods in the back end. Those are my routers. So Yeah, see, if I look, my 2 router pods, because I told you the HA proxy ingress router is really just it's just a container, have these same IP addresses as I cheated and put in my laptop's Etsy host because I didn't want to update my DNS. And you notice that the router is using the same address as the actual node that it's on. It's using that host network that we talked about. All right. So now I want to get back into the area where we created all these pods. All right, we should have some pods in here. So what I'm going to do is create another pod, and this one's going to be an oddball. I called it odd job instead of oddball. What this one is going to be sort of like the other one that was Hello OpenShift, only this time it's my own little customized Nginx. Notice it has tier equals front end, and we're running on a totally different port. Now, if we look at the service, we should, I hope, see that the service points to the 2 that we had earlier and this oddball, right? It's on a totally different port. It's a different application. Everything about the oddball is different. If we go and look inside the HA proxy config, all I did was created another pod. I didn't touch the route. I didn't touch the service. I created a pod, and boom, the HA proxy was automatically updated in order to load traffic to this new Nginx pod. And if I hit example.com, well, this time I went through HA proxy and I hit one of the OpenShift, Hello OpenShift. Second time, Hello OpenShift, since I'm not doing any kind of sticky sessions. The third time I hit that Nginx. So what this allows me to do is I could slowly cut down on the number of Hello OpenShift containers that are running, and I could slowly grow up the number of Nginx containers that are running. So that kind of shows like pods talking to pods talking to services, basic routes, and then how you can use those routes to slowly cut over from one to another. Troubleshooting of the SDN is very similar to the real world. Use the same tools, ping and TCP dump and those sorts of things work. There's a great troubleshooting guide to work through the steps. It also includes a link to a script you can run if you need to contact Red Hat to collect all sorts of network information so that one of my guys can take a look at it. Moving forward, we are working with the community, actually driving in the community, a move towards a better defined and standardized plugin interface to enable more third parties other than OpenShift SDN. Like I said, there are already vendors out there who have plugins, but it's sort of ad hoc, and so we're helping to develop a better interface for them. You can see all the work that my team is doing on the Atomic OpenShift networking board. I would say my 2 big things is the SDN, it generally just works. You don't need to talk to your network admins. You don't need any help from them. And the other one is don't be scared of the overlay and any CPU or throughput penalties until you know that it matters. For some people who need to squeeze every little bit across the wire that they can, it might not be great for you, but for the vast, vast, vast majority of us, the simplicity is generally worth that trade-off. And questions?
So Eric, yeah, we had a couple questions. One of them earlier in the topic. Is there any work being done to expose non-HTTP ports via router or some other mechanism? For example, if you wanted to expose a database that was running in a pod.
Yes, there is work that is going on there. That work does show up on that Atomic OpenShift networking board. I can't commit to any delivery dates, but the hope is that at least first stab, HA proxy will handle that TCP pass-through such that you could have the router doing the port forwarding for you. So yes, we are trying to address that.
And there was some chat going on, which I don't think is recorded, but there were a couple other really good questions in here. One of them was, how does the service IP route to the pod IP?
I actually have at the end of my demo, in case I had excess time, I was going to explain how that works. So the way that the service IP routes to the pod IPs one or more, changed just recently. The most recent versions are entirely IP tables based. The frames, or I guess at that point they're frames, that come out of the pod will they will get noticed by the host IP tables that they're going to a service IP. The host IP tables, and this is where I said it's a statistical round robin rather than a strict round robin, will pick one of the pod IPs and will do a DNAT to that pod IP. So that's the way that works, is it does a destination NAT. So when it shows up at the destination, the packet will show up with the destination pod IP and the source pod IP, which will then get forwarded back through and switched around the way the source needs it. So it's IP table space. We used to have a user space proxy that in user space terminated the one pod connection and opened up a pod connection to the destination, but now it's in IP tables, which is significantly faster.
Okay. So you showed a demo of sort of replicating external IP or external DNS space by using your Etsy hosts file. How does the internal DNS, how is it managed? And are we running services like DNS Mask?
Yeah, we are not using DNS Mask. Built into the Atomic Enterprise Platform Master is actually sort of a version of SkyDNS, which is automatically updated based on the pod information that's stored inside the master. So the Atomic Enterprise Platform Master is itself a DNS server and is providing that address resolution. So it might be possible for you to point your external resources at that DNS server, but then those external resources have to be able to participate in the pod network. They're kind of separate DNS spaces, but automatically managed entirely inside the master.
Okay, we have a few more questions. I'll try to get through them quickly because I know that we're going to run up to time in a minute here. So do we run SkyDNS? Is that in a pod, which is common across environments? And how do we point this DNS for every pod or service created?
Sure. The answer is Atomic Enterprise Platform does not run SkyDNS as a pod, although that is done in the Kubernetes world. It's actually a part of the OpenShift master, or Atomic Enterprise Platform master. Like that master binary has SkyDNS embedded inside of it. When a pod is launched, the kubelet, the binary on the node that launches pods, will inject, it gets Docker to inject that DNS server into every pod that gets launched. So you don't have to do any of that setup. It's automatic. It just pods come up and they'll be pointing at that DNS server, which will forward on as need be.
Great. And we had two kind of, here's another one. Is there VTEP that gets used to find pod IPs located on other nodes or VLANs?
I'm not sure I completely understand the question.
Yeah, I'm not sure either. I don't know what a VTEP is.
Yeah. No, we don't deal with VLANs at all in OpenShift SDN, right? It's only VXLAN tunnels, and there's no magic there, right? It comes into the OVS bridge and gets tunneled out of the box. No.
Okay. Okay, so then there's a couple questions that were related around isolation. So it was, can you do pod isolation to external data sources and databases? And you'd shown that pods can talk to other pods. Is there a way to stop that and strictly enforce pod-to-pod communications via services only?
Okay, that's a good question. For external access, the answer is no. If the node is allowed to talk to an external resource, the pods on that node, by IP, right, are going to be able to talk because they get natted to the node. We are actively working in the community to design an egress policy. So that it does not exist today, but it is something that we have tried to lead. It can be very difficult getting all of the network vendors to agree because everybody has their own view on what these things should be like. There are plugins that can allow a little more strict pod-to-pod communication, but I mean, they do exist, but at the moment it's pretty wide open. And again, that's an area that we're trying to lead in the community to design policies to better enforce isolation.
Okay. And if I had two, I guess another way, and to ask this in a different way, if I had two applications running, could I restrict traffic between those two applications?
With the default flat SDN plugin, they would be wide open. If they were privileged, there's not a good solution. There are, like I said, the things other than the default flat SDN, OpenShift SDN, that can do like project level isolation, not necessarily application level, but our default's pretty wide open.
Okay, thank you. And I'll do one more question, and then we'll close out the thing here. So it was a question about the master SkyDNS. Does that mean if you have SkyDNS on the master, does that mean if the master goes down, the services would not resolve, and that might prevent pods from talking to each other?
It is possible to run high availability multi-master, but yes.
But if you don't have it set up as HA, then you would have an outage there.
And it's down, you would have DNS out, yes.
Okay, great. So you want to go to the next slide, and we'll close this one out.
Oh, next slide.
So thanks again, everybody, for taking the time out of your day to join us. And a special thank you to Eric. Could you go back to the previous slide? I have a link on there. One more before that. So for other questions that you have, feel free to stop by some of our email lists, or you can talk to your TAM, forward questions to us. We're happy to answer whatever questions you have. I also like to thank Eric for putting the presentation together and the demo. Live demos are always very interesting to watch. And just a reminder that we have a whole series of webinars that we've been doing on Atomic Enterprise Platform, and you can actually check out the archive and our previous webinars as well as other interesting webinars from Red Hat at http://red.ht/containers-youtube. And with that, I wish you all a good day. Bye, everybody.